My name is Peter, and I work for Cake Solutions. We are a company focused on building reactive and data processing architectures using technologies such as Scala, Spark, and many others. And in this presentation, I'm going to talk about distributed stream processing. This area attracts quite a lot of attention these days, and I believe you will find next 40-45 minutes interesting. So what am I going to talk about? I will start with the motivations. What are the reasons behind this increasing demand of real-time data stream processing and how to address it? Then I'm going to talk about stream processing in general. Why do we care? Why should we care? What are possible use cases and also problems with that? After that, I'd like to talk about available frameworks, what are the similarities and differences, and also the typical use cases. Finally, we will conclude with some general guidelines and recommendations. I'd like to say this talk is based on my personal observation and opinions, which I have made when investigating how to deal with stream processing, and I'm definitely biased in some way. We are facing a huge increase in the amount of data we produce. We have produced approximately 8 zettabytes of data last year, so let's put it into context a little bit to make it more descriptive. Every minute we create 200 millions of emails, 48 hours of YouTube videos, and also we are able to query Google 2 million times. But the question is, how can we make sense of all this data? Because most of the data are not interesting, and also new data supersedes the old. And how is that all possible? Many new sources of data became available. For example, everyone has a smartphone, and every smartphone is full of sensors. Or the web feeds, thousands of pages are created every day. Or the social network, the huge game changer these years. Nearly everyone is exposed. I'm pretty sure we can find many other examples, but these new data sources also bring us new challenges. For example, the web and social feed mining, tremendous amount of useful information available, or real-time data analysis in general. We can do fraud detection, we can analyze trends, or we can do some kind of log processing and so on. So as we can see, there are so many options. And of course, stream processing is the answer, or the rescue. We want to process incoming data on the fly without permanent storage. The volume of data could be very high, so we are going to need a lot of resources for that. And also, we must be able to scale accordingly. And of course, we want to be able to react to events as they occur, as latency really matters here. So let's briefly talk about typical examples of streaming applications. Firstly, great example, ETL operations like joining, filtering, or various transformations of incoming data. So basically, taking data from a source, do the operations we want, and then send it out from the streaming system to something like Kafka or Hadoop or whatever we need. Or windowing, another typical operation. Windowing means we take an interval or window we want, let's say 5 seconds or 2 minutes, and then we perform operations on it like trending feed or trending sales. And other great examples of streaming applications can be like machine learning or pattern recognition. Machine learning is quite a trendy area these days, and of course we can apply it in the context of stream processing. We are able to do clustering, regression, or classification on incoming data. Also, pattern recognition might serve us as a great example. Sure, it is not as fancy as machine learning, but its applications like fraud or anomaly detection are definitely useful. Over the last few years, new architectures were developed to address various problems we have had. So let's have a look at the evolution of processing architecture. Batch pipeline has a large-scale database, such as HDFS, and many technologies to run batch analytics jobs over it. It works quite fine, but it's pretty slow. Popular attempt to address the slowness of batch pipeline is Lambda architecture. It adds a stream layer to get the possibility of real-time queries. So basically, we glue two different systems together, trying to get best of both worlds. Slow but accurate results from batch layer, and fast but somehow approximated results from stream layer. Problem is, we usually have to code it twice, which is pretty painful. Moreover, writing distributed algorithms is complex, and doing it for two different paradigms is even worse. There are a couple of tools trying to solve this, allowing us to write code just once, making things definitely better. But even if you can avoid coding your application twice, the operational burden of running and debugging two systems is going to be very high. So I take Lambda architecture as a reasonable solution from times we have no better tools available. But I firmly believe we can do better these days. So let's talk more about streaming, starting with basic standalone design, meaning we have an incoming data from various sources, which we can plug in directly to our streaming system, or as it is a little bit more common, we can use some kind of broker like Kafka and then do the processing. Or we can design our system in a way known as Kappa architecture. Kappa stores data in something fast that supports streaming. The stream is an immutable source of truth, and as well as the source of data for the other systems. The data can be processed, queried, or replayed, and finally end up in a data store. Each data store can be used as a source for separate queries with different characteristics and guarantees. As you suspect, distributed stream processing is continuous processing, aggregation, and analysis of unbounded data. It's a generally computational model as MapReduce, but we expect latencies in millis or in seconds. The systems are usually modeled as directly acyclic graph, DAGs, or DAGs. DAG is a graphical representation of chain of tasks, and we use it for description of the topology of a streaming job. I will help myself with terminology from Akka streams a little bit, but I think it will be clear anyway. So as you can see in the picture, data flows through chain of processors from sources to sinks, and this represents the streaming task. And speaking about Akka streams, I think it's very important to emphasize the word distributed, because even local solutions can create a dynamic DAG, but they are going to focus only to solutions running on multiple machines. When choosing between different systems, there is a couple of points we should take care of. So let's start with runtime and programming model. The programming model provided by the platform determines a lot of its features, and it should be sufficient to handle all possible use cases for the application. This is a really crucial topic, and I will come back to it very soon. The functional primitives exposed by a processing platform should be able to provide rich functionalities at individual message levels like map or filter, which are pretty easy to implement even if you want to scale a lot. And it should also provide across message functionality like aggregations and across stream operations like joins, for example, which are much harder to scale. For state management, most of the applications have a stateful processing logic that requires maintaining a state. The application should allow us to maintain access and update the state information. For message delivery guarantees, we have a couple of classes for that, like at most ones, at these ones, and exactly ones. Another important thing to consider. Failures can and will happen at various levels, like network partition, failures, or nodes going down, and so on. Platforms should be able to recover from all such failures and resume from the last successful state before harming the result. And then we have more performance-related requirements like latency, throughput, or scalability, which are extremely important in streaming applications. We should also take care of maturity and adoption levels, which this information could help us or give us a clue about potential support, available libraries, or even Stack Overflow answers, and so on. And also, last but not least, the ease of development and ease of operability. It's great when we have super fancy system which covers all of our use cases, but if we cannot write a program for it, or if we cannot deploy it, we are done anyway. Let's talk about runtime and programming model, which is probably the most important trait of the system because it defines its expressiveness, possible operation, and future limitations. Therefore, it defines system capabilities and its use cases. There are two distinctive approaches how to implement streaming system. First one, the native streaming. It means all incoming records, or events if you want, are processed as they arrive, one by one. Second approach is called micro-batching. Short batches are created from incoming records and go through the system. These batches are created according to predefined time constant, typically every couple of seconds. Both approaches have inherent advantages and disadvantages. So let's start with native streaming. The great advantage of native streaming is its expressiveness, because it takes the stream as it is not limited by any unnatural abstraction over it. Also, as the records are processed immediately upon arrival, achievable latencies of these systems are always better than its micro-batching companions. Apart from that, stateful operations are much easier to implement, as you will see in the next couple of minutes. Native streaming systems have usually lower throughput, and fault tolerance is much more expensive, as system has to take care of every single record. Also, load balancing is kind of issue. For example, let's say we have a data partitioned by a key, and we want to process it. If the processing of some key of the partition is more resource intensive for any reason, this partition quickly becomes the job's bottleneck. Splitting stream into micro batches inevitably reduces system's expressiveness. Some operations, like especially state management or joins and splits, are much harder to implement, as system has to manipulate the whole batch. Moreover, the batch interval connects two things which should never be connected: an infrastructure property and a business logic. On the contrary, fault tolerance and load balancing are much simpler, as system just sends every batch to a worker node, and if something goes wrong, it just uses a different one. And lastly, it's good to remark, we can build micro-batching system atop native streaming quite easily. And programming models can be classified as compositional and declarative. Compositional approach provides basic building blocks like sources or operators, and they must be tied together in order to create expected topology. New components can be usually defined by implementing some kind of interfaces. On the contrary, operators in the declarative API are defined as higher-order functions. It allows us to write functional code with abstract types, all this fancy stuff, and the system creates and optimizes topology itself. Also, declarative APIs usually provides more advanced operations like windowing or state management out of the box. I'm going to show you some code samples very soon. There is a number of diverse frameworks available, and it's literally impossible to cover all of them in just one session. So I have been forced to limit it somehow, and I decided to go for popular streaming solutions from Apache landscape. Therefore, we are going to focus on Apache Storm and its sibling Trident, and on streaming module of very popular Spark. We are also going to talk about streaming system behind LinkedIn named Samza. And finally, we will discuss promising Apache project Flink. I believe this is a great selection, because even if all of them are streaming systems, they approach various challenges very differently. Unfortunately, I won't talk about proprietary systems like Google Millview or Amazon Kinesis, and also we are going to miss interesting but still limitedly adopted systems like Intel Gear Pump or Apache Apex. So that's maybe for next time. Apache Storm was originally created by Nathan Martz and his team at Backtime in 2010. Later it was acquired and open sourced by Twitter, and it became de facto industrial standard in stream processing. Storm is a native streaming system and provides low-level API. Also, Storm uses thread for topology definition, and it also implements Storm multi-language protocol. This basically allows us to implement our solutions in large number of languages, which is pretty unique. And Scala is, of course, one of them. Trident is a high-level micro-batching system built atop Storm. It simplifies topology building process and also adds high-level operations like windowing, aggregation, or state management, which are not natively supported in Storm. In addition to Storm, Trident provides exactly once delivery semantics. And Trident has Java Closure and Scala APIs. As we all know, Spark is a very popular batch processing framework these days, with a couple of built-in libraries like Spark SQL or MMLib, and of course Spark Streaming. Spark's runtime is built for batch processing, and therefore Spark Streaming, as it was added a little bit later, does micro-batching. The stream of input data is ingested by receivers, and which creates micro-batches, and these micro-batches are processed in a similar way as other Spark jobs. Spark Streaming provides high-level declarative API in Scala, Java, and Python. Samza was originally developed in LinkedIn and as a proprietary streaming solution, and with Kafka, which is another great LinkedIn contribution to our community, it became key part of their infrastructure. As you were going to see a little bit later, Samza builds heavily off Kafka's log-based philosophy, and both together integrate really well. Also, Samza provides compositional API. And the last but not least, Flink. Flink is a pretty old project. It has its origin in 2008, but right now is getting quite a lot of attention. Flink is a native streaming system and provides high-level API. Flink also provides API for batch processing as Spark, but there is a fundamental distinction between those two. Flink handles batch as a special case of streaming, so everything is a stream, and this is definitely a better abstraction because this is how the world really looks like. So there was a quick introduction of the systems, and as you can see in the table, they do have pretty different traits. So now let's have a look at code samples, and of course, nothing is more important than counting the words. You know, word count is something like a hello world of data processing. So let's start with Storm, and please note the example was simplified significantly. First, let's have a look at this topology definition. As you can see, we have to define a spoke, or if you want, a source. And then there is a bolt, a processing component, which splits the text into the words. Then I have defined another bolt for actual word count calculation. Also have a look at the magic numbers, 5, 8, and 12. These are the parallelism hints, and they define how many independent threads and a cluster will be used for execution of every single component. As you can see, all is very manual and low level. Now let's focus on how is the actual word count bolt implemented. As long as Storm does not have built-in support for managed state, so I have defined a local state, which is far from being ideal, but good as a sample. Apart from that, it's not very interesting. It's just a simple Java. So let's move on and have a look at Trident. As I mentioned before, Trident is Storm's micro-batching extension, and Trident, apart from many other goodies, provides state management, which is pretty useful when implementing word count. As you can see there, I could use high-level operations like each and group by, so it is a little bit better. And also I was able to use Trident managed state for storing counts. And now it's the time for a pretty declarative API provided by Apache Spark. Also keep in mind, on the contrary to the previous example, which were really simplified, this is nearly all code you need to run this simple streaming word count. Every Spark streaming job requires streaming context, which is basically the entry point to the streaming functionality. Streaming context state configuration, which is, as you can see in our case, very limited, but more importantly, it defines its batch interval, which is set to 1 second. And now you can see whole word count computation, quite a difference. That's the reason why Spark is sometimes called distributed Scala. As you can see, it's quite standard functional code, and Spark takes care of topology definition and its distributed execution. And now the last part of every Spark streaming job, starting the computation. Just keep in mind, one started job cannot be modified. And now let's have a look at Apache Samza, another representative of compositional API. The topology is defined in Samza's properties file, so you won't find it here. But for us, it's important. The task has defined its input and output channels, and communication goes through Kafka. In our case, whole topology is word count task, which does all the work. In Samza, components are defined by implementing particular interfaces. In this case, it's a streaming task. I have just overridden the method process. Its parameter list contains all what's needed for connecting with the rest of the system. And the computation itself is just a simple Scala. And now let's have a look at Flink. As you can see, API is pretty similar to Spark, but notice we are not setting any batch interval. Computation itself is pretty straightforward. As you can see, there's just a couple of lines of functional calls, and Flink takes care of the rest. So now is the time to have a look at more interesting problems of stream processing, starting with fault tolerance. Fault tolerance in streaming systems is inherently harder than in batch. When facing an error in batch processing system, we can just restart failed part of the computation and we are good. But this is much harder in streaming scenarios because data are still incoming and a lot of jobs can run 24/7. Another challenge we have to face is state consistency, because in the end of the day, we have to start replaying events, and of course not all state operations are idempotent. As you will see, fault tolerance can be pretty hard, so let's have a look at how our systems deal with that. Storm uses a mechanism of upstream backup and recovery acknowledgements to guarantee that messages are reprocessed after a failure. Acknowledgement works as follows. An operator sends back to the previous operator an acknowledgement for every record that has been processed. The source of the topology keeps a backup of all records it generates. Once received acknowledgement from all generated records until the sinks, the backup can be discarded safely. At failure, if not all acknowledgements have been received, then the records are replayed by the source. This guarantees no data loss, but does result in duplicate records passing through the system. That's basically at least one delivery. Storm implements this with a clever mechanism of upstream mechanism that only requires a few bytes per storage per source record to track no acknowledgements. But in general, pure record acknowledgement architectures, regardless of their performance, fail in offering exactly one's guarantees, thus burdening application developer with reduplication. Also, Storm's mechanism is low throughput and has problems with fault control, as the acknowledgement mechanism often falsely classifies failures under back pressure. Spark streaming and its micro-batching semantics follows a different approach. The idea is terribly simple. Spark processes micro-batches on various workloads, and each micro-batch may either succeed or fail. At a failure, the micro-batch can be simply recomputed, as they are persistent and immutable. So basically, exactly one's delivery made very easy. Samza's approach is completely different. It takes an advantage of durable offset-based messaging system, is usually Kafka, of course. Samza monitors offset of its task and moves it when message is processed. Offset can be checkpointed in persistent storage and restored in case of failure. The problem is, when it restores offsets from the last checkpoint, it does not know which upcoming messages were processed, and it might do it twice. So that's at least one's delivery for us. Flink's approach is based on distributed snapshot, which keeps the state of streaming job. Flink sends checkpoint barriers, basically some kind of markers through the system, and when a barrier reaches the operator checkpoints corresponding part of the stream. So if we compare it to Storm, it's far more efficient, as it does not have to acknowledgement every single record, but does it in small batches. But don't be confused, it's still native streaming, conceptually it's very different from Spark, and also Flink provides exactly one's delivery. Most of the non-trivial streaming applications have some kind of state. On the contrary of the stateless operations, then we have just an input, processing and output. We have an input and a state, then we do the processing, and then we have output with a modified state. We have to manage our state, process it, and in case of failure, we expect our state to be recreated. The recreation of the state may be a problem a little bit, as we do not always exactly one's guarantee. Some of the records may be replayed multiple times, and this is not what we usually want. As we know, Storm provides at least one's delivery guarantees. So how can we achieve exactly one semantics provided by Trident? Conceptually, it's quite simple. You just start committing the records, but obviously it is not very efficient. So you start doing it in small batches. Then we do some optimizations, and here we are. Trident defines a couple of abstractions, which determines that when we can achieve exactly one's guarantee. And as you can see in the picture, there are some limitations, and it takes some time to dig into it. When thinking about stateful operation in stream processing, we usually have a long-running operator with a state and stream of records passing through it. And as we know, Spark streaming is micro-batching system and is implemented differently. Basically, Spark streaming manages a state as another micro-batch stream. So during the processing of each micro-batch, Spark takes the current state and a function representing the operation, and the result is a process micro-batch with an updated state. Sometimes solution for everything is just push it out to Kafka and problem solved. And it also works in the context of state management. Samza has real stateful operators, so any task can hold a state. And the state's chain log is pushed to Kafka. If needed, state can be easily recreated from Kafka's topics. To make it a little bit faster, Samza allows us to plug in key value store as a local storage, so it does not have to go to Kafka all the time. Unfortunately, Samza provides at least one semantics only, and it hurts a lot. But the implementation of exactly one's delivery is planned as I know. Flink provides stateful operators, conceptually very similar to Samza. When working with Flink, we can use two different types of states. First one is local or task state. It's the current state of particular operator instance only, and these guys do not interact between each other. Then we have partitioned, or if you want a key state, which maintains state of whole partition. And of course, Flink provides exactly one's semantics. So now let's have one more look how to count the words. This time will be more state focused. So let's start with Trident. You may have seen the snippet already, as it is very similar as before. We can create a state by calling persistent aggregate. Important argument is the count, which is built-in component for storing numbers. If we want to process the data from it, we will have to create a stream for that. As you can see, it's not very convenient. Spark's declarative approach is a little bit better. Firstly, we have to create RDD used as an initial state. Then we do some transformation or whatever. Then we have to define transition function, which takes a word, its count, and a current state. This function does the computations, updates the state, and returns the result. And finally, we can put all the bits together and get a state stream which contains word counts. Now let's have a look at Samza. Firstly, we need to define our state. In this case, it's key value store, and also we have to define how it should be initialized. And then we can use it during computation. As you can see, it's pretty straightforward, just a little bit more lines. And finally, let's have a look at Flink. Flink provides very neat API. We just call the function with state, which takes as an argument function with two arguments. First one is a word to process, and second is a state. Function then returns process output and a new state. I really wanted to show you some nice performance comparisons, but I will not. Horizontal comparison is a topic maybe for a whole talk, so I won't do it here. But a couple of guys did it already, so I'm really happy to reference them. But for now, just in general. When we talk about performance in streaming, we talk about latency and throughput. It depends on many variables, but in general and for a really simple task, if you are at 5K records per second per node, it's okay. If you can reach 1 million, it's nice. Over 1 million, it's great. And speaking about nodes, I mean pretty standard nodes like 24 cores and reasonable amount of memory like 24 or 48 gigabytes. For latency, in case of micro batch, we are usually thinking in seconds. In case of native streaming, we can expect latencies in lower hundreds of millis for most of the systems, but TuneStorm can operate in tens of millis easily. Also, it's important to keep in mind the cost of delivery guarantees, fault tolerance, and state management. For example, turning on fault runs may cost you like 10 to 15%, but in case of Storm, it can be like 70% of your throughput. So as always, nothing comes for free. During the talk, I've shown you stateful and stateless word count examples, and of course, stateless would be faster. In case you're wondering how much, so in the context of Apache Flink, difference was like 25%, but in case of Spark, it was around 50%. I'm pretty sure this could be tuned, but it could give us an idea. It is something we should have in mind. And speaking about tuning, all systems have very rich tuning options, which may lead to significant performance gains. And you should always find some time to have a look at it. Also, it's important to have in mind all operations are distributed, and sending data through the network is pretty expensive. So try to take an advantage of data locality, and also trying to tune up your application serialization. There's a lot to discuss about the performance, so I hope I gave you basic ideas what to expect, but we have to move on. When picking up the framework for application, you should always consider its maturity. So let's have a quick look. How does it look like in our cases? Storm was the first mainstream streaming system, and is used by many companies like Twitter, Yahoo, Spotify, and many more. Spark is the most trending Scala repository these days, and one of the engines behind Scala's popularity. Spark's adoption grows every day. It's used by companies like Netflix, Cisco, DataStax, Intel, IBM, and so on. Samza is used by LinkedIn and like tens of other companies. As an example, we can have like Netflix or Uber. Flink is still an emerging project, but we can see its first production deployments, and I'm sure more will follow soon. For example, I heard that Amazon was evaluating that right now. So we have just finished some basic comparison of chosen systems, and we discussed how do they approach various challenges which needs to be sorted out when implementing distributed stream processing system. Now you may have a quick look at a summary from my opinion, their key traits. And now is the time to move on to the last part of this talk, framework recommendations. I have to say this part is the most opinion-based by far, but I was really trying to be fair. So let's move on. The answer for the typical question, which one is the best or which one should I use, is, as always, it depends. So in general, always try to evaluate the requirements of your application carefully and be sure you fully understand the consequences of choosing a particular framework. I would also recommend you to pick a framework with high-level API, as it is little more elegant and more importantly, much more productive. Also keep in mind the most of streaming applications are stateful, so the state management of a particular framework should be up on your evaluation list. I would also recommend go for a framework with exactly once delivery semantics, as it makes things definitely easier. But of course, this really depends on particular requirements. There are definitely use cases when at least once or at most once semantics or guarantees are all you need. But also keep in mind, systems supporting exactly once does not have to support weaker guarantees. Lastly, make sure your system is able to recover quickly. You can use CauseMonkey or similar tools for testing. Because, as we discussed, fast recovery is crucial in stream processing. So, and now let's have a look at particular frameworks. Storm is still a great fit for small and fast tasks. If you care mainly about latency, Storm might be a good way to go. But also keep in mind the fault runs or Trident state management hurts the performance loads. Interesting option might be a potential update to Twitter's Heron, which is designed as a Storm's replacement, and it should be better in every single point, but it also keeps the API. Problem is, there is no guarantee Twitter is going to open source it, so who knows if this is a really good idea. For Spark streaming, you should definitely at least try it if Spark is already part of your infrastructure, because in this case, streaming comes basically for free, and you can also take advantage of various Spark libraries. Also, if you really want to use Lambda architecture, it is a pretty decent choice. But you should always keep in mind micro-batching limitations and be sure latency is not critical for you. When thinking about adopting Samza, Kafka should be a cornerstone of our architecture. I know it's pluggable, but nearly everyone, maybe everyone, is using Kafka, so I will stick with that. Also, as mentioned before, Samza is shipped with powerful local storage, and it can handle states in tens of gigabytes easily, which is pretty nice. But keep in mind Samza's at least one delivery limitation. Flink is conceptually a great streaming system which covers very most use cases, and it often provides progressive functionality which might not be implemented by its competitors. So you should always consider Flink when you need a functionality which might be hard to implement Spark or in general in any other micro-batching system. And apart from that, Flink has an API for common batch processing, which may be pretty useful. But you need to have enough courage to adopt emerging project, and also don't forget to check out its roadmap. And the last thing I want to mention today is Dataflow and its open source initiative. Dataflow is part of Google Cloud Platform, and Cloud Platform has all sorts of things in it, as a huge data store, BigQuery, Cloud PubSub, some tools for data analysis, and so on, and also aforementioned Cloud Dataflow. It's Google's managed service for batch and stream processing with unified API, and it's built upon well-known Google technologies such as MapReduce for batch processing, from Java for programming model definition, and Millwheel for stream processing. And all of them are really good. But you may be asking why I'm talking about that. As I said, I will be speaking about open source framework, and this is clearly Google's proprietary solution. But Google decided to open source Dataflow SDK recently, and guys both behind Spark and Flink have implemented its runners. So now we have an ability to run jobs-defined Dataflow API in Google Cloud Platform, in Flink, or in Spark. And it's also possible that more engines will follow soon. Dataflow provides API in Java and in Python, implemented by Google itself. But I have also found 2 DSLs in Scala, implemented by community. Apart from that, Google and a number of partners submitted this as a new Apache proposal named Apache Beam. So it seems as a pretty interesting option, but it's very important to emphasize all of this is very recent, and the implementation of some of the promised features might be missing. So now it's time for questions. So do we have any? But I think I'm a little bit behind the schedule, so just find me somewhere and we can discuss various things later. So just find me. So thank you very much for your attention. I hope it was helpful for you. And also we are hiring. So if you would like to join us, just follow the link. We do pretty interesting stuff in Cake. That's all from me. Thank you very much.